Let's compute the eigenvalues and eigenvectors of this matrix that we were looking at before, 1, 2, 2, 1. So, first step is to look for the eigenvalues. And so for the eigenvalues, we look at the determinant of A minus lambda I. Now, this is going to look like 1, 2, 2, 1 minus, and then we're multiplying lambda against the identity matrix. So that means, oh, and we're taking the determinant of all this. So that means we're taking the determinant of 1 minus lambda to 1 minus lambda. So in other words, we've effectively just subtracted lambda from the diagonal. Now, using the formula for the determinant of a 2 by 2 matrix, this is going to be 1 minus lambda squared minus 4. And so we need to find the roots. So we multiply this out and we get lambda squared minus 2 lambda minus 3, which factors as lambda minus 3, lambda plus 1. And so we have two eigenvalues, 3 and minus 1. And I've called those lambda 1 and lambda 2. It doesn't matter what order you number them in. I just want to label them so that I can keep track of them for the next step. The next step is to look for the eigenvectors corresponding to each of these eigenvalues. So let's start with the first one, lambda 1 equal to 3. And so in this case, we're looking at solving the equation a minus 3i times x equals 0, the homogeneous equation. And so we solve that by row reducing. So a minus 3i is going to be 1 minus 3, 2, 2, 1 minus 3, which is minus 2, 2, 2 minus 2. And so when we go to row reduce this one, well, this is a simple enough matrix. You can see right away that it's 1 minus 1, 0, 0. And so then that means that x is going to be 1, 1. That's what we will take. And in other words, E sub 3, the eigenspace corresponding to eigenvalue 3, is the span of 1, 1. So let me just back up there a little. In case it's not clear where I came up with x1, I did the mental calculation to see what vector is orthogonal to this row right here. So if I do a dot product between this row and the vector 1, 1, then I get 0, and 0 is the first entry right here in this equation. That's what I'm solving for. If you want to back up even further, then recall that if we convert this back into the system of equations that it represents, the first row says x1 minus x2 equals 0, and then there's no pivot in the second column, so it is free. So we take x2 to be t and resolve as x1 equals t, x2 equals t, so that x equals this vector right here, and I pull out the common factor of t. And I just need an eigenvector, right? I don't need to describe all of them. So I take, in this case, t equal to 1 to make it as simple as possible. And so what I've actually found here is my vector, this guy by himself, forms a basis for the eigenspace. Okay, and so that's how I come up with 1, 1 as my eigenvector. So maybe I'll call it V for eigenvector. How's that? Okay. And then that's just for the first eigenvector. We still have to do the second one, so let's look at lambda 2, which is minus 1. And so in this case, I'm looking at a minus negative 1 times I, which means I'm adding 1 to the diagonal. So now it looks like the matrix 2, 2, 2, 2, which immediately row reduces to 1, 1, 0, 0. And so my corresponding eigenvector is going to be 1 minus 1, or minus 1, 1, whichever, doesn't matter. Scalar multiple of an eigenvector is always an eigenvector, so it doesn't matter where you put it. Actually, you know what? I'm going to change it around, and let's see. So if this is my solution to the original equation, then I'm going to take my second eigenvector to be minus 1, 1. So I take t equal to negative 1. And the only reason I did that is because that's how I presented it when I talked about this example back at the beginning. And so now you can check, just as we saw before, that if we multiply this guy, we get 3 times this guy. And if we multiply the other guy, minus 1, 1, then we get negative 1 times minus 1, 1. And so that's the point of exactly the eigenequation. So this says a times v1 is lambda 1 v1, and this says a times v2 equals lambda 2 v2.